Hello, YouTube family. Haven't done any video in a while. It's been raining, it's been cloudy, it's been everything in California, so I haven't really had any time to do any imaging. But luckily, I did have some older data that my friend Jim captured with the same telescope as mine, slightly newer version, a Ricardo Hondas 200, of a very interesting supernova complex that's widely been imaged. It's very popular. It's called the Veil Nebula. It's also referred to as the Cygnus Loop. It's a supernova remnant. Many people have identified and has been cataloged for a while. The source of the supernova was a star 20 times more massive than our sun that exploded around 10,000 years ago. It is an incredible sight to be seen. And at the time of the supernova, it would appear brighter than Venus, and it was visible in the daytime. So something that's very interesting. It's 110 light years across, so it's huge, and it has many different subnebulas like the Western Veil Nebula or the Network Nebula or the Pickering's Triangle and so forth. I've done videos on almost all of them. But today, let's look at something more wide field. This is quite big in the night sky, 6 times bigger than the full moon. So if you can imagine how big that is, you'll understand why it takes a little bit of a wide field to capture it all. Some people captured it in 400 millimeters, 500 millimeters. I captured it, Jim did, at 600 millimeters with a full frame camera. So let's take a look at the telescope and let's see what we have. So this is a telescope. His is a little bit newer. It's got athermals, so a slightly different mirror, and a carbon fiber body, so it's lighter. And he's using a different mount. He was using an Ioptron, a Skywatcher Orion HDX. So Skywatcher EQ8 or Orion HDX, same mount. Pretty good mount. Not as advanced as the Ioptron CAM120. It doesn't have the ports and the capabilities, but can carry a lot of payload, and it's all made out of steel. So it's very, very good. Now, this is, for comparison, the same imaging train as mine, a QHY600 at the back. He has a QHY filter wheel, just like I do. And he has a FLI Atlas, where I have an Esato 3.5 inch. But we have the same field of view. We have technically similar fields of view. The interesting part is the athermal one that he has worse stars than the MK1 version, the first one, which is mine. He has a little bit more aberration than this one. No idea why. I'm really, really happy that my scope is the way it is. Although it has fungus, it does have better correction, I suspect, or maybe he collimated mine better than his, I don't know. But anyway, 200 millimeter aperture, the size of the mirror, f3, really fast, and 600 millimeter focal length with a full frame camera that gives you a massive field of view, about 3 degrees. So let's take a look at the data. So this object is rich in O3 and O2. There's some sulfur, but it's kind of pointless to do it. Now, this is about 10 hours per channel, I suspect. And I think it's about 600 millimeter spot exposures. You can see the stars are pretty good in the center, but as you go towards the outside, it starts to be a little bit deformed. And, this is fine. It's within the spec of the telescope. He might have had some tilt here that he corrected after, but it's actually incredibly good for a full frame sensor on a telescope like this. Now, we were struggling with flats. I think we eventually got it working well, but the O3 data, remarkably well behaved. Not as noisy, very clean. Look at the filaments in the Network Nebula. This is really good. This is an 8-inch telescope that really goes to show you the detail that this mirror can collect, this little light bucket. And it's just incredible to look at. Now, what I will be watching for is, if you guys saw my previous video of the Network Nebula that I did, this hydrogen alpha filament has been obsessing me. It's very faint. It's very hard to get. I managed to capture with my RC in like 20 hours in 2x2, but this is very beautiful. Like, the detail in the hydrogen is really beautiful. I didn't even know this little nebula existed here. So, you get shocked by these little light buckets and the amount of data you can collect. This data is collected in a Bortle 7 sky, so it's equivalent to a small town He lives in San Jose, not really that small, but it's pretty light polluted. So not the best sky conditions, and the details are really good. The veil itself, the western veil, the witch's finger, whatever you want to call it, is actually really good as well. And the filters he used are Astrodons in this situation. But look at the star here, Caldwell 22, I believe it's called. If it's not, please correct me. No flooding, no halos, no nothing. Just incredible, incredible details. Now I'm going to do another check on the O3 because that's the one that everybody has issues with. Is there some haloing here? Not really that visible. So this is the data, about 20 hours. Should be great. Let's take a look. So I stacked the data, and as you can see, there's some flat issues, some kind of color problems with the oxygen channel. Flats are kind of hard with this scope. You really have to get the values right to get it working, the mean values for each. Now I'm talking about pretty advanced stuff, and if you don't understand it, please feel free to let me know and ask me. When you capture data in mono, you have to kind of calibrate this data, especially for space, and you have to take what's called flats, flat field images, where you actually put a light panel, or you can use the sky or any kind of light source to kind of remove the vignetting that comes from your imaging train, the telescope and camera. So it's not that easy. There's a rule of DSLR flats where you do it at a third of the histogram, not so easily at a very, very sensitive element, camera like this, and that's why it can be a hassle. You can do 1x the number of electrons that are captured, the mean, or you can do 3x and 2x. It's hard, then you have to experiment. But anyway, so this is the stack. I didn't do anything, I just stacked it. Let's take a look at what happens next. I believe this has blood exterminator applied. I think so. As you can see, as you get towards the corners, the stars start looking funny because of the way the scope and the correction that comes with it. But this will go away as we move on. So I stacked the data, I stretched the data, I removed the green that comes with it, and I did some S-curves in there. The data is just very, very, very clean. Yes, there's gradienting. Yes, there's weird patterns from flats, but I'm not worried about that. I can process around them. Again, the network nebula, really clean. I've applied the high dynamic range transform, so it doesn't look as blown up. Same here, the detail's really good. Again, for a small telescope, really impressive. Not much to see with the stars. This is just the stars extracted. As you can see, it's actually funny that you see where the objects are. There's dark space. So I did that because I was going to process the nebulosity and then come back to it. So this is the mask I used to kind of clean some of the stuff up, but I didn't do much to this image. Usually hydrogen, oxygen data doesn't really need that much. I just stretched it a little bit, cleaned it up a little bit, and let's see the final result. So let's start with the starless image. I really emphasized on cleaning the outer edges. It's very hard to clean this perfectly, but I was really happy with the result. Again, with these really fast telescopes, flats can be hard to do, and they will not, sometimes it's hard to correct everything. So starless image looks amazing to me. I like the details, I like the nebulosity. Let's see how well it cleaned up when it goes to the final image. So in the final image, what I did is brought back the stars like I usually do with the pixel math algorithm that I usually use, and it's all in my other videos if you're curious. And maybe that's it. I think I did the small S-curves to pull some of the blacks a little bit back and kind of darken the image, but this is, to me, a very, very good Cygnus loop. It has all of the benchmarks of a great image. The nebulosity is there, the star size is there. The stars are just big enough to see, and they don't interfere with the nebulosity. Again, the more data and the faster your telescope, the more stars will impede in the way of showing nebulosity. That's my goal. I want to show the emissions in space, not the stars. I'm not trying to detect planets, but to show you the beautiful formations of gas that are out there. So this image again uses hydrogen for red and oxygen for blue and green. It's a HOO image, as astrophotographers refer to. I think it's a pretty stunning example of what you can do from really a pretty bad sky, a pretty bad light polluted sky, and from your backyard. You don't have to travel to the desert. So let me know what you think. If you think that this image could be better, I'd love to hear your feedback. And until next time, clear skies.